So this is my topic. And just to quickly introduce myself and introduce what we do, we are a fabulous system on chip design house based out of Chennai, incubated at IIT Madras. And I'll briefly describe what system on chip is and what fabulous means, right? So, how many of you remember the computers of the 90s? The big clunky boxes, yeah. That entire system on the board getting shrunk into a single chip is what we call a system on chip. And what does fabulous mean? It means that we purely design the chip. The whole semiconductor industry is split into design and manufacturing. So nobody who designs actually manufactures, and nobody who manufactures actually designs, even if they work for the same company. So Intel, for example, designs and manufactures their chips in-house. That's called an IDM. But the foundry division and the design division are separate. Most other companies you've heard of, NVIDIA, AMD, Apple makes their own chips, of course, so are all fabless. They do not own their own foundry. The three that I named use the same foundry that we do, among others. So we are incubated at IIT Madras, and we also have approval for the second chip that we are developing from the government of India under the design linked incentive scheme. So there's a lot of support that we get from that. We call our brand Mindgrove Silicon. It's not just chips that we make. We also make boards and we make other things. We make modules for people to deploy single board computers and so on. But the chips themselves are branded under the title of Mindgrove Silicon. Our first chip is a high performance microcontroller. In a sense, not really relevant to the topic here because it's meant for controlling small devices. But it can run certain things. The second family is called Vision SoC, and it is an edge vision chip. It's not a full compute chip, but it is an edge vision chip, and it can do a lot of things that you guys might be interested in. And a little bit about myself. I'm not going to apologize for saying I'm an AI skeptic today. You'll see why going on, and I swear that this has relevance to the topic we're going to be discussing. I'm an electronics engineer. I did a lot of work in ultrasound, in X-ray, in a lot of vision processing. That's been my passion. So what am I doing building chips? I am an electronics engineer. I've done everything in the stack from JavaScript down to pushing atoms together. And right around the time of the pandemic, we ended up in a situation where I wanted to build something. I wanted to build some imaging devices. I did not find the chips for it. And we were staring at each other, trying to figure out what to do. Professor Kamakuti, who's now director, he was not director of IIT Madras back then, but he's now director of IIT Madras, basically encouraged us to take that matter into our own hands, showed us a bunch of other people who are having the same problem and said, basically, you guys have the ability to do this. Why don't you get a chip out? So we started doing that. As a result of having started a semiconductor company in the year 2021, just as the AI boom was picking up, everybody came to me and said, will you make an AI chip? Or what AI chip are you making, to be more precise? And here I am. I will tell you stories about why I am, but I don't believe in, or I don't blindly believe in the AI promise. However, I'm a hopeful AI skeptic who sees real possibilities and real potential, and I really want to solve the problem of problems that I see with current gen AI. And I think that one of the keys to building that out is to go to work on the hardware. And this is why I'm an AI skeptic, okay? I will go over the story. This is what we grew up with. I'm a kid of the 90s. This is what we grew up with, right? This is what we thought AI would be. Scary, in one word. It would be mathematically, logically brilliant. How many people remember pretty much every science fiction story had an AI that would say, does not compute? We expected that they would be extremely literal. And this is from War Games, but the alternate picture that I wanted to use was Captain Kirk talking to a computer and shutting it down with logic, which happened about once every 3 episodes. And we also expected that they would be unemotional, very, very straight. And HAL 9000 is a classic case, emotionally stunted. And really, all the AI horror that we have been fed and all the AI promise that we have been told was out of things like this, right? How much has our cultural ethos about where we are going to go with AI been about this? But that's not what we ended up with. This is what we ended up with. We ended up with an AI which can draw and paint and color, which can make movies, which can write scripts, um, which bullshits. We did not expect that we would end up with these guys which would. We thought it would be literal. It is not. It bullshits all the time, and it can't do simple math. What's going on with this, right? And part of what is happening here, it is cognitive dissonance for me, and I kind of dived into it to understand what was going on. And what happens is actually what we're looking at is a kind of um, architecture, a way of dealing with data, which is extremely statistical and extremely probabilistic. Therefore, it is approximate, and because it's approximate, it ends up not being exact and accurate as we expected it to be. Part of that happens to do with foundation of logic that we chose. One of the foundations of logic that we chose, which is the floating point arithmetic, which there is an entire, I think it's a 90-page document which says what every programmer should know about floating point accuracy. But that's not the only thing, right? Um, it's a brilliant tool. We have a. I'm just going to talk a little bit about just India, just talking about who we are, where we are right now, and what we're going to talk about, what we're going to build for ourselves. Leave alone the way that people are trying to deploy AI in the rest of the world. Let's talk about what the promise for us in our economy is. We have a huge population. The word population got lost there. I don't know. We have a huge population. We are very successful in a lot of things, but we have very low productivity, which is keeping value locked up. This is exactly why I see that promise. We need to go into a higher value economy and not just be doing base work. I see automation, not just automation at the physical level, not just robotics or not just assembly line automation. I see automation at the level of intellectual work also as a promise to be able to move up this productivity value ladder. One of the things that I used to do is so the last session was about nuclear power, right? And I used to work with the organization which was presenting earlier, and we used to supply some things for them. It has been so long since I saw that particular diagram and very nostalgic. But having worked in that field, one of the things I learned is that you can't be 70% accurate. You can't be 90% accurate. You have to be 99% accurate. Forget about false negatives. False negatives are zero, and false positives are 0.1%. That's the scale that you expect. You pitch an algorithm which is 75% accurate generates 25% false positives and misses a few things, they will reject it. Nuclear power, aerospace, all of these are not healthcare. These are not places where we can afford mistakes. And what we are looking at when we do that, sorry, I will come to this. What we are looking at when we do that is we are looking at other kinds of algorithms. We're looking at not just LLMs. And that is basically what I'm trying to say over here. Now, one thing that science fiction got right about AI needs power. How much power? Lots and lots of power. There is a certain um, attractiveness to the idea of using the demographic dividend and not doing that monkey work, right? And not deploying an expensive AI resource to do this stuff, right? I can employ 20 people at even decent wages. All they need is this much power. One full meal in the afternoon, a little breakfast, and a little lunch. How much does AI need? Google is literally trying to build a nuclear power plant. So, if we want more accuracy, it takes more power. If we want more power, we need, in a country like India, which has power problems to begin with, where are we going to get it? So, there are ways around this, and there are ways to go over this and build around this. And why I think it is important is because of this very simple reason. We were doing inspections of um, aerospace casting components maybe about 7 or 8 years back. And you have assembly line which is turning out, let's say, thousands of components an hour. And there's this guy sitting and x-raying each of these components. Already the manufacturing line is so good that you get maybe only 1 out of 1,000 pieces which are defective. You do not want to miss that one piece. This guy is sitting there and watching these things go by one after the other, one after the other, one after the other. He has his job is to flag when he sees that something is. What happens is the guy gets tired and he starts making mistakes. And so the inefficiencies start creeping in. You need more people to do it. You need people sitting and doing this, highly trained resources sitting and doing this. And we need that accuracy to come in, which means we need to deploy these kind of things. Or do we? Yeah, do we have enough power? The thing is, the way that we built today, if anybody has, I know a lot of people have deployed models at the usage side. But if you go back, you will see that the base of pretty much everything we do today is that equation on that expression on top, a dot x plus b, which is a matrix multiplication offset by constant. We do everything as matmul, and the reason we do everything as matmul is most of the operations, like 95% of the operations that we actually want to do, are reducible to a matmul. And the reason why we want to reduce it reduce it to a matmul is because me, as a hardware engineer, I will tell you this: you guys can come up with the algorithms as fast as you want, including me. I can come up with the algorithms as fast as I want, but to build a chip, forget the design process for a minute. Just to take a design and fabricate it on a wafer of silicon, just imprinting the design on a wafer takes about 3 months. And then there is all of the logistics time, packaging it into the little plastic box with the metal leads that you see, or the ball grids that we see. That's called assembly. And then there is another phase of testing those chips. And then there is all of the supply chain side of shipping it from the foundry to a fabless semiconductor entity's office. And then you actually build the boards, put it on a. You're talking about 6 months, 8 months delay easily. I can't ship a patch. And so we try to get down to the bare basics of the kind of hardware that we can actually build, which can be deployed generically to all of the applications that we want. It so happened that there was one architecture never built for AI, never built for computation. It was built for an entirely different kind of computation, which got deployed almost accidentally to compute for scientific applications, and that was GPUs. We, growing up, used GPUs to play games. And at one point of time, this is around 2007, I believe, NVIDIA guys see a science lab in Europe buying, I think it was CERN, but don't quote me on that, I don't know for sure. I don't remember for sure. They see somebody buying a bunch of GPUs. And Jensen Huang is very curious, and he directs people to go and ask them what is going on. So it turns out that they're writing GPU shader code to do scientific computation. From that, the idea of CUDA was born. I've used CUDA to process scientific data, to process ultrasound data, to process X-ray data. I've used CUDA for rendering. I've used GPU for rendering. Then it turned out that one of the things that you need to do for really good GPU rendering is matrix multiplication. And the guys who were building neural networks found that they could easily adapt the math to become MATML friendly. And then they deployed it on GPUs. It was really good. It worked really well. And it just basically that's how it took over the world. Even the GPU is capable of a lot more than matrix multiplication. That's how I used it. It's capable, for example, of Fourier transforms. It's capable of other kinds of computation, which is what we used to do with it. But it creates a couple of other problems. It hugely, because you're doing MATML, you need to have that dense matrix of numbers, X by Y grid. And you have several, the layers of a model are each sets of numbers, sets of matrices which get multiplied successively and applied to the input data, right? So models become big. A lot of the places where we want to deploy, a lot of the places we want to automate, you cannot have a 70 billion, even a 7 billion parameter model, right? Even if you're using a single 8-bit data type to encode a 7 billion parameter model, that is 7 gigabytes of memory. Now, it's not just a question of storing that data. It's a question of taking it out of wherever you're storing it, bringing it to the processor, running the algorithm, pulling the next piece of data, pulling the next piece of model out of the data store, running the model. So that's why you see chips becoming faster and faster. That's why you see people trying to race down to 2 nanometers and 1 nanometer. Because the smaller your chip is, the smaller your transistor is, the faster it can switch. And so you're just trying to shove data as fast as you can into the compute pipeline. And the compute pipeline itself is fast enough. The problem is the data coming to the pipeline and the data going out, which takes power. So you can choose to do two things about it. You can choose what algorithms you deploy, the kind of algorithms you build, and you can choose the kind of architectures that you build. Right now, up to now, the algorithm side has been moving so fast that it's really hard, like I said, because it's at least 6 to 8 months, even if you have a ready design to put it into production. By in 8 months, a new algorithm has come out, and the hardware, a fine-tuned piece of hardware, has become obsolete. So the hardware engineer's dilemma is this: do I build for now, or do I build for 2 years down? If I'm building for 2 years down, uh, how do I predict what is going to happen 2 years down in a field that changes every 2 days? But um, we have learned a lot in the last 10 years of design for AI, starting from the GPUs, and Google started building tensor processing units. Um, and I will come to the TPUs in the next one. But right here, we have many other techniques besides LLMs, right? We have all of these things. These are considered AI: support vector machines, convolutional neural networks, RNNs. All of these are considered to be AI. Even a decision tree is considered to be AI, and it's a hugely useful piece of equipment. I'll use an analogy to the human body, right? Let's say I'm throwing this thing and catching it. How much of uh, the action of throwing and catching actually went to my brain? There is a hand-eye coordination which is happening, but it doesn't. I'm not reasoning it out. I'm definitely not putting it into language and throw it and catch it. When you catch a ball, you just, right? And let's say you touch something hot and you pull back. What is happening there? That's a spinal reflex. There are still neurons over here. There's still intelligence happening. It is not cognitive. Language is used only in the up here. Not everything reaches up here. So if you think of the kind of systems, let's say you're deploying an industrial system, let's say you're deploying it in a nuclear reactor, again, to give a lot of the systems need to react at split seconds. You don't need to take all the data back out to the central processing system and bring it all the way back as control. What you need to do is you need to have reasonable intelligence happening at the edge. So incidentally, one of the things that we did, one of the reasons that our microcontroller is 700 megahertz, it's high performance, is so that it can do this kind of work at low power at the edge for small amounts of data, even for maybe a little bit of audio, but no more than that. So you need zippier stuff. Here, I will put on my skeptic hat again a little bit and say that I don't necessarily agree with provisioning very large neural processing units on microcontrollers. I'm going a little bit deep into the weeds over here. I just want to make this point. I don't necessarily agree with that yet, because they become generic, they become big, and they become impossible to deploy at the cost factor that you want on the edge. But this is the kind of thing that we need to look at in terms of whole system architecture. Give you another example of vehicle, right? A car. We have ADAS. Right now, driver assist systems, pretty much the vehicle architecture is made up of what is called a domain controller. So you have one controller for the powertrain, you have one for the brake, you have one for, let's say, the steering, the lighting, the infotainment. The automotive world is moving to a kind of architecture called a zonal architecture. So where you have compute unit for the front left, front right, back left, back right, center. And if you have a brake over here, that is controlled by this zonal controller. If you have a brake over there, that's controlled by that brake controller. But you have brakes and lights controlled by the same thing. And here we run into a problem called mixed criticality. The brakes are more critical than the lights. The engine is more critical than anything else. The engine is more critical than the infotainment, for example. So, but you have all of these things running on the same device. So, how do you solve for that? Um, Here again, it's a question of how we design these systems as hardware engineers to be able to handle this mixed criticality and such that one component does not affect the other. So that is in terms of algorithms. You can do any number of things to select algorithms. You can select algorithms which are less complex, which get the job done. And for example, there was one recent, not so recent, maybe about a few months ago, piece of research that I heard of using an LLM to train a classic um, algorithm and get its weights and its and get a fixed function accelerator trained with its weights and everything else so that it can actually tackle the job at hand. But you use a use an LLM or use a CNN or a much higher form of AI, more cognitive form of AI to train the lower form of AI. That's actually intriguing to look at. In terms of architectures, in terms of my domain, right, my current domain, we have three ways of doing this. There is the fixed function accelerator, which is what Google calls a tensor processing unit. Um, the most famous of this is the systolic array. There are other forms such as vector engines, which is something that I like a lot. And there are a bunch of other fixed, like you can literally fix the math over there. Now, what is happening with the TPUs is they're really expensive to make. Only Google can afford to make them. And they're really impossible to program for anybody who is not like Google level engineer. The other problem with the TPU architecture today is that you get a 100 tops TPU. This paper which I'm talking about, which came out of Google, which came out of which was supported by Google, and it was collaborated by the guru of computer architecture, David Patterson. Um, they found that the current generation of TPUs at that point was using only 20% of the operations that were provisioned in the compute system. The rest of it was just going to moving memory up and down. So you build a really powerful TPU, you build a very powerful fixed function accelerator, but then you're not able to get data to it. What's the point? So is that the best way? If you can get the data to it, it's probably the most efficient way to do it. As long as you're digital. I'll come to that. The GPU style, general purpose, GPUs have a reputation for being hard to program. But trust me, they're easier to program than this stuff. To date, a lot of people have tried to do training on fixed function and training on TPUs and systolic arrays. And I'm seeing a lot of people, I used to see a lot of people saying we are going to build for that. And over the last couple of years, accelerating over the last 6 months, I've seen a lot of people giving up on that dream and saying, we're going to use the fixed function accelerator purely for inference, and we will train on the GPU. GPU still to date, nobody has found a replacement for the GPU for training. The third there are other ways of doing it. The third one, which is interesting to me, is neuromorphic computing, which is kind of mimicking the structure of the brain. The fundamental difference that you should know between the systems that we have built to date and deployed and the human brain is that the human brain is analog and it is multi-signal. There is no single signal path. So neuromorphic computing attempts to bring that analog nature of the human brain to silicon and uses very old techniques dating back to the 1940s of doing analog computing. It will sip power compared to the stuff that we have right now, but it is incredibly hard to build, and there are no products out yet. Unfortunately, to date, all the neuromorphic algorithms, neuromorphic designs that we've seen are very fixed function, and they're not generic enough that you can deploy it on anything else. So, no products are out yet that I know of which are implementing neuromorphic computing. So, yeah, a little deep dive into each of these things, what I just went over. This is what a GPU looks like. This is what a current generation NVIDIA GPU looks like. This is a block diagram of the Google TPU. And you can see that big matrix multiply unit, 64K per cycle over there. But you see all of this hardware around it to feed it with data. And all of this hardware around it is the stuff that really burns power. Yeah, neuromorphic. So this is the promised land. This is what we want, where we want to be, right? We can. There are decades-old techniques which we can deploy today. We don't need to only look at the latest algorithms. There are decades-old techniques which are um, available to us to be able to move forward. Our algorithms are moving fast, and hardware is obsolete as soon as it hits prototype, forget market. Inference is still possible. Now it is becoming more possible to build specialized hardware for it. I would not touch the GPU in terms of training yet. We've seen a lot of hype. I think we are at the top of the hype cycle. We're coming a little bit down. But the hopeful skeptic in me says that the plateau of productivity is in sight, and we just have to hold on and get to the point where it is actually feasible to do really interesting deployments, and actually see some real long-term value gain out of this. Yeah, thank you. Uh, yeah, the last point I would leave you with is better, more efficient hardware is the way to get there. Thank you.